Bismillah ar-Rahman ar-Rahim. We will discuss electricity. It is somewhat a silly chapter, however, it contains many important items that may be asked in the exam. First of all, the static electricity and electrical potential. The word electricity comes from the word electron, which is a Greek word explaining what we call Ampere. Ampere is a substance. Whenever I rub it with some other substance, suppose we have two substances as plastic and rubber, we rub both of them with each other. One of them gains more electrons than the other. So as we can see at the end result, there is a potential. This potential creates what we call static electricity, which is important during anesthesia. Whenever we use the inflammable anesthetics, such circumstances can lead to inflammability and explosion accidents. So this is what we call the static electricity. Substances are classified according to their conductor to electrons and to insulators and semi-insulators and conductors. The difference is the easiness of how they transfer electrons. Carbon is included in of course with metals as conductors. Semiconductors like thermistors and diode, they conduct electrons less than that of course conductors, but they need some sort of energy to make the electrons move. This makes a difference. Photodetectors is a transducer. As we see, it can change the energy source from light to be an electrical form. It is the form of it's some sort of a semiconductor. Whenever radiation falls on this device, the electrons collect this radiation energy, and they can increase their activity to send electrical signal. And this is what we use to obtain what we call a photo detector sensor. A magnetic field is created when suppose we have a coil and we have a wire moving through this coil. If two coiled wires are attached to each other and each of them has an electrical current, they will display each other. This electrical current created by the movements will yield what we call a magnetic field. There is a field around it which can exert forces on other materials. Electrical or magnetism, it is a form of activity of small particles of the electrons, which will yield some sort of energy affecting others. We have what we call also electrical flux, which it's more than the magnetic field. It has a density, and its unit is Weber. The magnetic flux density is called Tesla, which is Weber per square meter. For a nice knowledge understanding, we must know that the magnetic field of the Earth is yields around 60 micro Tesla, and the MRI apparatus yields from 0.2 to 4 Tesla. Ferromagnetic materials are materials that liable to be to possess a magnetic properties. Whenever this ferromagnetic materials is being applied in the core of a wire, a coiled wire, the movements of this ferromagnetic can yield a magnetic field. Direct and alternating current. Of course, direct currents goes straight forward in one way. Alternating current goes forward and backwards, like the normal circulation of the human being. And we have, of course, a source of direct currents as batteries and as thermocouple. We have, of course, rechargeable batteries, and we call it second cell, in which we can recharge the battery by shifting the direction of the current. On the other hand, the primary cell battery, which is the battery which are not being charged, cannot be charged. If they are charged accidentally, they can be a source of explosion and heat. As you can see from the figure, the direct current goes in one direction, and the alternating current is creating a sine wave, whether positive or negative, and sometimes the current can be containing the two types of current. The Ampere, which is the Systemic International system unit representing the current of electricity, it figures out 6.24 time 10 to the power of 18 electrons per second per some point. And this is the amount of electrons passing in 1 second past a point. Of course, we will never forget the 6.2 0.22, which is the Avogadro's hypothesis figure of 1 mole. Of course, the other one has the 10 to the power of 23, but 1 ampere is 10 to the time of 18. This is the definition of ampere. It's the path of the amount of current per point per time. We can see from the figure the principle of galvanometer. Whenever we have a magnetic field and we have a source of electricity going in a coil, as we can see, it is formed in a jeweled way and is supported by a coil from downwards. Whenever the current passes through this wire in perpendicular to the magnetic field, this movement of current will make the jeweled barring displaced. This displacement will give a hint about the amount of current used. So this is the principle of the galvanometer. Pointer on a scale, we have a hair coil to balance the movements of the bearing jeweled. Magnetic flow meter, which is important regarding one of the methods to measure cardiac output. As we can see, we have a magnetic field. The magnetic field is made of coil. Whenever, of course, they electrify, they will create a magnetic field, and we can represent the flow of blood of the RBC through a tube, as we can see. The flow of blood through this tubing, which is supposes the blood vessel, perpendicular to this magnetic field, will create a potential. This potential is going to be recorded by two electrodes CD present across the blood vessel. Of course, blood vessel, this we will measure the flow. The velocity of blood, of course, is affected by the diameter of the tube, which is, of course, not constant. So that the net result is the flow will be average, not the mean flow. So this is the principle of the electromagnetic flow meter. The volt, as we can see, which is the electrical potential between 2 points, it is calculated by dividing the power in watts over the current in ampere. As you can see, the V, we have the opening of the V upwards, and the W, we have also the opening of the W. We call it double V in French. We have the openings are face upwards like the V. On the other hand, the denominator, which is A, we have the opposite. So this is a way to remember or memorize what we call that the volt equals the power in watt and over the ampere. We have an example of the correlation between the power. As we see, we have a direct current and we have a current of 4 ampere creating 96 watt energy by lighting. Of course, watt is what we call energy expansion, yani energy per time. So whenever I want to find the potential energy, which is the volt, I can divide both over each other when we'll create the end result with which is 24 volt. In other words, as we can see that the volt is the potential difference when a current of 1 ampere of a substance in a substance when the rate of energy expansion is 1 watt, yani 1 volt, and the rate is 1 watt. We can define the potential difference, which is the volt. Of course, electricity creates heat energy, and this is why we use it as regard using lamps. This figure downwards, it's before what we are going to talk about. However, it's the difference between the alternating current and the direct current. For interest, nothing more. You can see that the alternating current creates a sine wave, a positive and negative, and it has a peak. Like the dynamic compliance and the static compliance, it has a peak. The peak is around 340 volt, though the main is around 220 volt. And as we see, we have another source of direct current, which is 240 volts. So this is to show the difference of the graph between the two types of current in correlation time to the potential relationship between both, so that we will later on understand how can we compare both types of current. So the alternating current has a peak and has a maximum amplitude and has an average, but the direct current has an average, not a peak. To compare two types of currents, we compare them regarding the heat production of both of them. يعني عندنا two currents, and then we want to compare of both of them to create the same heat energy produced. So we use what we call a RAM. We call root main square to compare the two roots. In other words, as we can see, to make the two currents similar to each other, to make a proper comparison, we can see the alternating current, and then how we square it Why we do we square it? So that the negative sine wave will be positive, and after we square it, we create the mean المتوسط. After that, we go to do a square root to reach to the final Ram's potential, which we can easily compare it with a direct current. Of course, all this is just knowledge to be known, so that we know what's the meaning of RAM. The most important thing is the electrosurgical equipment, which is the thermi. As we know that the direct current, all the alternating current has a frequency of around from 50 to 60 hertz. This current is capable to induce a ventricular fibrillation. But in surgical equipments, we use a frequency more beyond that this limit in order not to make the patient face an electrical insult causing ventricular fibrillation, so that we can use currents up to 1 megahertz, which produce negligible affection on the incidence of ventricular fibrillation. But at the same time, this current is capable to cause heating, and this is the purpose of using such equipment. The electrosurgical equipment, which is the thermi, has an active electrode used by the surgeon to touch the area. This area, of course, the current density is high, so that it induces clotting or a cutting. At the same time, this current must go back to the station through what we call the conductor element that touches the patient. احنا بنقول accidentally بنقول على عازل، انما هو مش عازل، ده موصل. What's the meaning of موصل? It makes the current go through it so that it can go to the station. The current must complete the circuit. Whenever this plate is covering a wide area of the skin and it's properly attached to it, the current density of the current passing all over this area is very minimal. But if this plate is not placed properly on the back of the patient, of whatever is site of attachment, the current may go through a very minimal amount of the skin, so that its density will be high, causing burning. This is why a patient can develop burns post-operatively from accidentally putting the plate. Of course, sometimes if we use faulty apparatus, this electric current can go through the electrodes of the skin and cause burning at the site. This is why whenever we have a surgical field nearby the electrodes, try to put the electrodes far away. Also, the current accidentally can pass through low resistant pathways as processes in the human being. If you must put in your mind all such insults that can occur. Of course, electromechanical equipments cause waves which can interfere with the ECG waves. Of course, if this plate is completely dissociated from the patient, the current, whether it's touching the patient or not touching the patient, must pass through a port. So it may pass by the electrodes. It might pass by the patient touching an earthed equipment. يعني العيان لامس الكشافات, the electrical lighting of the theater. If he touches and there is a fault, this current can pass through the hand touching the earthed equipment and can induce burning at the site. Of course, the most liable parts to be burned is the finger and the part of the nose. And here's the figure showing the electric equipment and the neutral plate, and how is the current being dispersed all over a large area, and the current must go from the active electrode going back to the electrosurgical unit. Of course, we have two types of diacetyl. We have a monopolar and we have a dipolar. What we were discussing is the monopolar, that we have an active electrode and we have a neutral plate, so the current will go through this circuit. The bipolar electrode, as we know, the current goes through one of the parts of the equipment and returns back to the other part, so that we are not in need of a neutral plate. This will decrease the incidence of burn. At the same time, it can be used with a patient having an artificial pacemaker. I'm sorry, but it's the main advantage of it is precise. This is why we use it in neurosurgery, so that we can be precise at the site, so that we'll not injure the nearby subject. This is the figure showing the types of electrical components of an electrical circuit, so that whenever I can see the inductor, how does it look, and the capacitor, how does it look, and the difference between the inductor and the resistor. The inductor is made of a coil, but the resistant is some sort of a wiring, and we have two resistance, as we can see, and we have the earth, and we have the transformer, two coils separated by some sort of a wiring system. All this are the types of electrical components. Capacitance. A capacitor, it is an apparatus or two conductors separated by an insulator. The main use of it collects the current. It collects the electrons. Whenever the electrons, especially the alternating current, passes by it, it collects and then release. Direct currents, it collects till it is fully saturated and stops the current. So it works finely with alternating currents. So a unit of capacitor is the column C. A column, representing what's the meaning of column, which is the electrical charges contained in the capacitor. It is the quantity of electrical charge which passes some point when 1 ampere flows for a period of 1 second. You have a current of ampere passing a point in 1 second. You know, of course, amount of ampere, as we had said before, we multiply it by the seconds, so that we can get the column. The more we have amperes, the more we have the time in seconds, the more we'll have electrical charges contained in this capacitor. In other words, the farad, which represents the capacity of the capacitor. How does it work as a capacitor? Whenever the capacitor is attached to a potential difference, it will collect currents. Equation, F equals C over V. C column goes for column and V goes for V. So we can say that farad has a CV, We will never forget that it is the C over V. A capacitor, we can define the capacitor in which the 1 volt difference increases the column added to it. Whenever I increase the volume, the volt, there is more column attached to it. This is the side equation also to memorize that the volt is W over A, because this figures we must combine to reach to a final decision sometimes. The defibrillator is an equipment mainly made of a capacitor, as we know. So that the benefit of it is that whenever I use the capacitor, I can find electrical charge being stored in it, in this farad capacitor. This electrical can be charged speedily so that it will cause synchronization of the heart, regaining the normal SA node heartbeat. So the defibrillator, we have a capacitor and we have an inductor. As we know before, the inductor is a coil of a wire. Whenever I applied 3000 volt across this capacitor, it collects 160 millicoulomb, so that the energy of collection equals potential V times Q. V times Q. This how can I figure out the energy required to collect this amount of energy whenever the volt difference is 3000. You see? Of course, when we see delta E means the difference. We can see the defibrillator in the figure when it is working, the switch is on or the switch is off, and the current passing to the heart. Of course, the two plates, one on the sternum and one on the right, under the right clavicle. The end result, the potential equals Q over C, as we said before. Q over C. End result to memorize, or you don't have to go through all these figures. It depends about تفاضل تكامل. So the end result is whenever you want to figure the energy required for this collected charges in the capacitor to be released to go to induce what we call the defibrillation, we apply half of this dose time the amount of electrical charges in the capacitor yield with 3000 volt. We find the end result is 400 joule. 400 joule. This is the amount of the capacitor of the defibrillator. Of course, not all this energy is being subjected to the heart. Part of it is being stored in the inductor. This is why we have an inductor. The current is square-like. The current release is square-like. It's around 35 ampere. Of course, most of the defibrillators nowadays are monophasic, not I'm sorry, they are biphasic. Monophasics that you are given, first of all, the 360 watt 3 times. But the biphasic, the current goes and returns back, so that we need the half of the amount I mentioned before. Of course, it is less traumatizing to the heart. This is what we call the biphasic. Of course, electrical charges are not just stored in the capacitors. It also can be stored on the supposed glass container of the bobbin. Whenever the bobbin goes up and downwards, it creates a static electricity which can make it stick. This static electricity can be a source of origination of flammable anesthetics. Capacitor interference, of course, as we can see from this figure, as understanding some knowledge, why do we have interference on the ECG most monitors? Because we can represent the lamp, the bulb lamp, as a part of a capacitor, and the patient is another part of the capacitor, and in between the gear is the insulator, so that we can have we have created a capacitor. So whenever the current frequency is 50 hertz from the bulb, this 50 hertz will create a current. This current will interfere with the ECG, as we see from the screen. This is why we have interference. Nowadays, some monitors can cope with this interference. Of course, as we said, the inductors with capacitors, all this in the electrical equipments can affect the end result of the monitoring system. We must put in our mind and the interference. We call it sometimes inductive coupling. You see, the way of getting rid of this noise. Whenever I want to have a proper signal, I must make a signal noise ratio difference high, so that the signal will be more than the noise, displacing much better results on the screen. So sometimes in as we know, the ECG electrodes are made of metal, and we have some sort of gel to enhance the conduction. Sometimes we apply a sheet of woven, this is special material around the electrodes. This woven is attached to the Earth, so that when there is an interference, it will be taken by this woven material attached to the Earth, leaving the normal electrodes to do their work. This is what we call a signal to noise ratio. As you can see, but also the patient is doing an X-ray, and we have a transformer. This transformer is creating a current. This current will affect the ECG monitoring. How can we improve this noise, this signal noise ratio? By what we call averaging. It is a system. It is computerized in most equipments. This averaging takes the normal. We have two signals: the interference and the normal signals. It averages the abnormal signal to zero, and it knows it comes every now and then, not continuous like the ECG. So whenever it causes averaging to the noise to be zero, it improves definitely the signal. This is what we call averaging. Resistance, as we know, ohm, it is a potential over ampere. The more the thinner is the wire, the more the resistance is more. Most resistors are not affected by the frequency. We can see here the strange gauge. We have this is what we use in direct measurement of the arterial blood pressure. We have a diaphragm, and we have a strain gauge, a piece of wire which is under pressure. When the mechanical movements of the blood affects the diaphragm, it induces inclination. This wire will slang, and the resistance of it will be affected. From this change in resistance, I can know the pressure. The most important second item in this subject, apart from the electromagnetic flow meter and the defibrillator, what we call the Williamson Bridge. Williamson Bridge is a four-armed bridge which is attached to a power source, as you see, a battery. These four arms create what we call null deflection. No current is going. What's the meaning of that? Whenever R1 over R2 equals R3 over R4, I mean resistance, the deflection will be zeroing. It will be null deflection. This is the normal, as long as R1 over R2 equals R3 over R4. Suppose we want to measure the resistance of a subject. I put it on R4. You see, انا مش عارف المقاومه بتاعت الجهاز بتاعي، فبحطه في R4. النال ديفليكشن هيحصل له خلل. طب ارجعه ازاي؟ to use what we call rheostat on R3. Rheostat is a changeable resistance. I change it so that the pointer will return to a zeroing point. The amount of being changed from R3 can give me hint about R4. What's the importance of a Williamson bridge? It is a system to measure change of resistance. Most of the instruments we have as a strain gauge, we have something inducing change in something. The mechanical power of the blood had changed the resistance of the wire. If I know how much this resistance of the wire is, I can predict the blood pressure. So this is the Williamson bridge, which is incorporated in most of the instruments to measure the change in pressure due to change of other subject. This is another way to measure also the resistance. We have, as we see, 5 resistors, and we have a potential energy. The 5 resistors, of course, when I use the 5 resistors to measure the potential, it will differ between both. You see, so whenever I want to apply a resistor, these resistors are equal, first of all. So if I want to to know one of the resistors, I don't know. I want to know a resistor, so I apply it in one of these 5, and then I began to create a connection between it and others. If they are much changed than the normal, I can evaluate the resistor. So this is why this is another method to measure resistance. The difference between impedance and resisting of any wire is not affected by frequency, but impedance is affected by frequency. This is the point. This is the point. So most of the equipments used as the ECG, we have an amplifier has a resistor. Most of them has a high impedance than the skin impedance. Of course, we are trying to minimize the skin impedance by putting KY gel so that the signal will be much improved. But we put in our point that we are afraid of electrical interference. We're afraid of electrical surgical interference that may cause affection, heat problems. So most of this figure is showing that the potential created by attachment, whether the impedance of the amplifier is high or low in comparison to the skin, to yield a better configuration, so that it's better to have a high resistance of the amplifier with a low resistance of the skin, so that we can get a proper signal. Of course, when the skin is moist, definitely it will connect current much better than the dry skin. The moist skin, interesting, is due to sympathetic activity. So whenever I have a sympathetic activity, I find the skin is more moisture. This is measured accordingly by what we call galvanic skin response. So we can know from this moisture the activity of the electrical of the autonomic system. Of course, the subject chapter is tough. It has too much equations and too much definitions. But the most important thing to know, to have a knowledge about what's going in the theater, what's the diathermy, what's the defibrillator, electromechanical flow meter, the Williamson bridge, the strain gauge. All these are very important for us as anesthetists. I hope that I had fulfilled as much as I can. And you must, of course, read this subject several times to understand it well. And thank you very much. Wassalamu alaikum wa rahmatullahi wa barakatuh.